5.4, the fundamental theorem of calculus. We're going to be talking about area functions. So we're going to, previous sections, we took the integrals. We said that it was always height times width, and we were doing indefinite integrals. But now, because I want to find area, I'm going to use the function notation with a capital A for area. And notice that my lower bound is a constant a, my upper bound is x. And in this situation, these x's are my independent variable for the area function. And then these t's for the height and width parts of the integral, we call it a dummy or a placeholder variable. It could be anything, but we usually use t. It's just a placeholder variable. So then from here, we have to talk about, well, why is it a to x? We're going to always evaluate from some constant a, and then we don't know from what interval we want to go to. It could be any kind of x that we're going to be able to plug in. So if I want to be given, we're going to be going from 0 to an x, I can say then evaluate for the area when x is 2, when x is 5. That gives us a setup of the basic area function. So here it is formally written out, the area function, and the key thing on this one is that the left endpoint is a. Got that, lower bound. Unknown right endpoint of the area. I also want to say that this gives us the net region, the net area for the region we want bounded by the graph and the axis. So for example, in number 11, we're given a graph, don't know what the function is, so they give us that a of x is going to be from -2 to x of f of t dt, and f of x is going to be given with the bound of 4 to x of ft dt. So from here, if we want to say for a, evaluate a area when x is -2. So I'm going to go ahead and insert -2 for my x as an upper bound. And I'm going to be going off the graph. But we have to remember when the upper bound and lower bound are the same, we did not move, so there is no area to compute. The answer would be 0. For b, if I want to evaluate the f function when x is at 8, I'm going to insert 8 for my upper bound. So I'm going from 4 to 8 of f of t dt. And I can see then when I look at the graph, I'm going from 4 to 8, and my area is given under the x-axis as 9, and since it's below, it's going to be a negative area of -9. I'm going to go ahead and do C, which is evaluating a function when x is 4. So I'm going to evaluate -2 to 4 for the integral. And then I can see from -2 to 4, I have areas of 8 plus 17, and our answer should be an area of 25. I want to go ahead and move on to the fundamental theorem of calculus, part 1. There's 2 parts. We actually have to go ahead and we're clarifying that the area function is what we were doing. But now it's saying in this part 1 that if we take the derivative of the area function, or in a sense, remember, I could take the derivative of both sides of this equation, and the derivative of a would be a prime is equal to the derivative of the integral. And it turns out, if I'm taking the integral, which is the antiderivative, if I take the derivative of the antiderivative, I should end up equaling the function itself. So if I want to go ahead and try to prove this real quickly, if I am starting from any interval from a to some x, but I want to go ahead and say I'm going to go from x plus h, some h. I don't know what the h width is. I moved from x. So I'm doing this whole entire big area, which is then the area of x plus h I'm evaluating. And then if I'm going to go ahead and say, well, if I just go from a to the x, this area is a of x. And if I want to go ahead and figure out the piece I did not include in the second step, saying I want this piece, I'm going to use that this is the height of f of x. And this width here is h. So area would be height times width there. And it would make sense if I take the entire area, subtract part of it, I should be approximately equal to what we had not included in the second part, what was left. And if you notice, I have an h in there, but I'm going to go ahead and divide both sides by h. And I now have that the function is approximately, and it looks like the difference between the two areas divided by the width. And this is closer looking to the difference quotient when we were using limits. So if I take the limit of both sides as h is approaching 0, because this is the time when I want this width to get next to as close to as 0 as possible, to get as infinitesimally small as possible rectangles under the area, then I should get as exact of an area under the curve as we could. So that from here, we learned back when we were doing limits, this is the derivative. So this entire side of this equation is really a prime of x. And the limit as h approaches 0 on the right-hand side, because f of x then does not include an h, it's f of x. So the derivative here is approximate to the f of x. And this then proves that these undo each other in a sense. Opposite operation, the derivative of the antiderivative should be equal to the area. This is a big concept that we want to be able to use in a little bit. We're going to go ahead and we're going to move on to the second part of the fundamental theorem of calculus. And we're given here that f of the derivative or the antiderivative, the integral of this function from a to b is equal to the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. And from here, we should be equal to the area. So we're going to keep using this notation. And the other key thing is when we could rewrite this, that we want to evaluate the antiderivative, and it could be denoted as the lower bound, upper bound that we want to use. So this is another way of denoting it. So it means the derivative of the integral is the function itself. So we have to make sure that we apply this. I'm going to go ahead and do a couple of examples. Number 21, if I'm given f of t equals 3t plus 1, and a is going to be equal to 2. We want to go ahead and find the area function from a to x of f of t dt. So what we're going to do is I'm going to go ahead and using the second theorem of calculus, I'm going to go ahead and take the antiderivative of this, which should be, oops, I'm going to set it up correctly first. I'm going to put my lower bound in as 2. I'm going to put my function in. And now I'm going to go ahead and take the antiderivative, which would be 3t squared over 2 plus t. And it's not plus c anymore. This is now a definite integral. I'm going to go ahead and say my bounds, and I'm going to use the second part of the theorem to calculate this. So I'm going to calculate f of b, or the upper bound, which is, it means I'm inserting an x. And this is f of b, and I'm going to subtract f of a. So then when I go ahead and evaluate this, inside the second bracket should be 8, so I'm going to be minusing 8. And this then is my antiderivative evaluated with a definite bounds of 2 to x. I'm going to go ahead then, it said, all right, check that the antiderivative, so I'm going to take the antiderivative, or I'm going to take the derivative of this, what was boxed, and I have 3/2 x squared. Remember how we find the antiderivative, or the derivative, I'm sorry, is we take the exponent down in front as a multiplication and subtract 1. And the derivative of x is 1, and the derivative of -8 is 0. So from here, it simplifies into 3x plus 1, and the original function was 3t plus 1. So this is the same as the original function. Let's go ahead and do another one. I can do 35. Given that we go from -2 to 2 of the function of x squared minus 4 dx, I want to find its antiderivative. I'm taking the integration. So I have x squared, adding 1 divided by the new exponent minus 4x, and I'm evaluating at -2 to 2. Using FTC part 2, I'm going to plug in my upper bounds into the function, and I'm going to subtract the lower bounds of the function. And I'm going to go ahead and evaluate this, and I should get negative, 32 thirds. Let's do another problem. 45. If I'm given the integral from 1 to 2 of 3 over t dt, I want to go ahead, that constant rule says I can pull that multiple out, and I have from the bounds from 1 to 2 of 1 over t dt, and now if I want to take the antiderivative of it, it's 3 times ln of t evaluated from 1 to 2. So I'm going to go ahead and plug in ln of 2 for the upper bounds and minusing the ln of the lower bound. Simplifying, I get 3 ln of 2, and remember ln of 1 is 0, so this is then my answer. Trying another one, I'm going to do 48. I have the integral from 0 to 1 of 10 e to the 2x dx. So I'm going to do the same process. I'm going to pull that constant multiple out, 0 to 1, e to the 2x dx. I'm going to find the antiderivative, which is e to the 2x divided by 2. And I'm going to evaluate this from 0 to 1. So I have that coefficient or the multiple of 10 out front, evaluating e, plugging in the upper bound, and I'm going to be plugging in the lower bound. And I see from here that I get, looks like 5e squared, and then if I multiply the 10 into the -1/2, I get, I'm sorry, oh, did that one wrong. All right, let's try number 61. We're given that the d of dx of the integral from 3 to x of the function t squared plus t plus 1 dt. This is finding the derivative of the antiderivative, but we're evaluating at, I gotta get this done. So we're going to go ahead and we're really, because it's undoing the function, but we're evaluating at the upper bound, my answer should be x squared plus x plus 1.